Testing on YouTube. 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 All right, we got it working on YouTube. YouTube works fine. Now, the last one, Twitter, or X, as they like to call it. All right. Then we need to wait for 8. How's it going, everybody? Let's get this horn here ready. Hey, hello from Neuralink. How's it going, XR7RKE? AKA one of the decentralized nodes that is running the Neuralink emulator. Neuralink isn't a real person. Neuralink is a distributed compute grid that emulates a person known as Neuralink. Let's open up with this. Thought on the TeslaBot tactile sensor. That's not original idea, so I haven't really looked into it, but the TeslaBot tactile sensor is basically similar to there was an MIT paper probably over a decade ago at this point that basically had a camera, like a little cell phone camera, and then they had some gel, and then basically rather than using some kind of capacitive sensing, which is how a lot of touch sensors used to work, or pressure sensing, they basically look at the image from this camera through the gel, and basically the gel deforms, and then you can basically get touch using a camera sensor, which sounds weird, but it's actually a great way of doing it because cameras are very cheap and you get a lot more high resolution. So I think that TeslaBot or the Optimus robot and Tesla going into that kind of touch feedback based on camera sensors seems like a really good solution. But it's not original. That's like an old idea that they repurposed. How's it going, Ed? Okay, I think it's already 8, so let's blow this horn and get started. Alrighty, everybody. Welcome to another Hoopo stream. As you can see, I got this hat on because it's December and it's winter and the holidays are going to be coming up, so this is actually going to be the last of 2 streams for this year, this one and the one tomorrow. So we're going to try to make them good for you guys. Here we got today's stream is about distributed inference and fine-tuning. So you can find the links to all the different things that we're going to do here. Actually, let me refresh because I added some more links. But this is on a GitHub page called Stream Docs, which you can find all the information for each of the streams, including these nice thumbnails. I used to use Midjourney for these, but now this is a DALL-E 3 image. It's not even DALL-E 3. What do you call the OpenAI ChatGPT DALL-E? Do you call it Chat DALL-E or something like that? IDK. But mostly we're going to be looking at 2 different papers here that are in a very similar kind of vein. So the first paper is called Distributed Inference and Fine-Tuning of Large Language Models over the Internet. 13th December 2023, and this is coming from a variety of different institutions and groups here. We got Hugging Face, which is everybody's favorite. I don't know if they're the favorite, but it's an open source startup that basically hosts models. And then you also got this Yandex here. So Yandex is a Russian technology company providing internet-related products and services, including search engines. So it's basically kind of like a Google of Russia. I don't know much about Yandex, to be honest, but it seems like a bunch of these people are from there. And then, of course, you also have Tim Detmers kind of out of nowhere. This is the guy who does all the quantization papers, so interesting to see him on the author list, and when he's on there, the paper's going to be good. So that's the first paper we're going to look at. The second paper we're going to look at, and props to Neuralink, one of our community members, for posting this one. This is the 2nd December 2023, so just slightly older, and this is coming out of Google DeepMind. So Google DeepMind is the group originally coming from the acquired company DeepMind, now part of Google, and then Google's kind of like mashed all of these teams together. Google Brain, Google DeepMind, they're all kind of now the same team. And this is called DiLoco. Di for distributed, low for low communication, and then co for, I guess, low communication is loco. Training of large language models. These papers are slightly different, but they're similar in flavor, so we're going to look at both of them. How's it going, Minotaur? Okay, so let's start with the abstract. We're going to have to go through both of those for both of these papers. Large language models are useful in many NLP, which is natural language processing, which is the way that people used to describe the kind of text, language, translation kind of world, all those kind of family of tasks. I feel like people don't really talk about NLP anymore. It's kind of like a dying term, but I guess they can use it here. And become more capable with size, with the best open source models having over 50 billion parameters. For example, Llama 70B would be an example of that. However, using these 50B plus models requires high-end hardware, making them inaccessible to most researchers. So most people aren't using the Llama 70B. They're using much smaller models such as Llama 7B or even the Mistral 7B. Because their GPUs just aren't big enough to really even hold these larger models. In this work, we investigate methods for cost-efficient inference and fine-tuning of large language models, comparing local and distributed strategies. So inference is whenever you're actually using the model to perform some kind of user or product service, you know what I'm saying? Like actually answer a question that some user has. And fine-tuning is more when you have a small data set and you're basically changing the language model weights, or often just training a little specialized adapter that will then make that new fine-tuned language model better at some specific task. Comparing local and distributed strategies. So local is whenever you're training it at home on your GPUs, or maybe at your work with a setup that you have locally. Maybe you can actually go and touch it. And then distributed means that it's spread out all over the internet. So yeah, there isn't really formal definitions of local and distributed, I guess. Like, is local, does it count as local if you're training it from one building over? Or is that distributed? If it's over 2 buildings, is that distributed? If it's 2 computers in the same room, is that local or is that distributed? I don't know, those definitions are kind of a little hazy, but largely it means either kind of all in one place geographically or not all in one place geographically. We observe that a large enough model can run efficiently even on geo-distributed devices in a consumer-grade network. This could allow running LLMs efficiently by pooling together idle compute resources of multiple research groups and volunteers. So here they're kind of... This isn't the first time that people have done this. I think a very long time ago, I remember that you could, for example, donate your computer CPU, and then you could have this process running that whenever your computer was sitting idle, it would basically use the CPU on your computer as part of this larger distributed, decentralized compute machine that would then... I think what they actually did was protein folding, but I'm not 100% sure anymore. But this idea of basically pooling a bunch of disparate hardware that kind of is provided by individual people and maybe small companies that have smaller clusters, and then getting it all together so that you can run one giant kind of compute job. People have been kind of doing that for a while, I guess. You can even think of the internet as instantiation of that same idea. One of the earliest papers is HiveMind. There you go. We address 2 open problems: how to perform inference and fine-tuning reliably if any device can disconnect abruptly. Right, so that's going to be an issue, right? If you have this giant heterogeneous cloud of compute, people are going to be turning off their computers randomly. People are going to be adding stuff randomly. So, like, you have to be very fault tolerant. How to partition LLMs between devices with uneven hardware. So here they're talking about introducing this concept of parallelism, right? We're going to go into it, but parallelism is the idea that you have different parts of the language model and then the data that you're using to fine-tune that language model, and how you split that up between different devices. Devices here refers to like one GPU or multiple GPUs within one server. How do you do that in an efficient way, accounting for communication overhead? That's what this entire paper is about. Joining and leaving at will. In order to do that, we develop a special fault-tolerant inference algorithms and load balancing protocols that automatically assign devices to maximize the total system throughput. We showcase these algorithms in Petals, a decentralized system that runs Llama 2 and Bloom over the internet with up to 10x faster than offloading for interactive generation. These numbers don't necessarily mean anything. So here they're saying 10x faster, but that's 10x faster compared to some other completely kind of like arbitrary system, right? You're going to see similar claims here where it's faster than some other thing, but it's hard to really directly compare these things, and they're going to be faster in certain setups than in other setups. So anytime you're doing these kind of load balancing or optimized distributed computing setups, they're going to be optimized with respect to a specific setup, right? So like if you were to make the latency much higher, then a different optimal solution would exist. If you were to have a setup that has all of the same device, then a different setup would work differently. So there's so many variables here that there isn't a single solution to this optimization problem. There's hundreds of different solutions, and you're going to basically have to find the most optimal solution for your given setup every time. This is just one type of solution. We evaluate the performance of our system in simulated conditions and real-world setups spanning 2 continents. So probably Europe and the US, if I had to guess. Society is just one distributed model, man. Yeah, we're all just basically distributed compute nodes. We really are. Okay, so that's the first paper. Now let's read the abstract for this second paper. Large language models have become a critical component in many applications of machine learning. However, standard approaches to training large language models require a large number of tightly interconnected accelerators. So accelerators and devices, that's the same thing, so just the GPUs. And here in Google, right, this is a Google paper, so it's a slightly different flavor than the Hugging Face paper. Hugging Face is kind of an open source organization. So in their situation, they're more trying to figure out a way to do distributed training and distributed inference when you have this large cloud of a mishmash of different GPUs that are kind of coming online and leaving at different times, and you have to be much more fault tolerant. Versus here in the Google world, you're dealing with a giant data center that has 700 million, maybe not 700 million, but has like a huge amount of the same exact TPU, right? So you're basically dealing with a different system. You have much faster speed of communication, and then you have a much more homogeneous compute topography because all of your TPUs are basically the same exact chip. So slightly different setups, which means that you're going to have slightly different solutions. Exchanging gradients and other intermediate states at each optimization step. So here they're saying any training process is going to be a series of steps, right? Training iterations is basically one step, and you're going to have hundreds of thousands of millions of steps to get to a final trained model. And in between each of those steps, you're going to have to basically communicate things like gradients, which are basically how much you need to change little parameters within each of those neural nets. You're going to have to communicate those between the devices. So doing that efficiently is a hard problem. While it is difficult to build and maintain a single computing cluster hosting many accelerators, it might be easier to find several computing clusters, each hosting a smaller number of devices. In this work, we proposed a distributed optimization algorithm, distributed low-cost communication, or low communication, that enables training of large language models on islands of devices that are poorly connected. So here, reading in between the lines here, what are they talking about? They're basically saying Google has a bunch of different data centers in different countries, right? And then each of those data centers has a bunch of chips that are all well communicated within each other, but then they're not communicated kind of to each other, if that makes sense, right? So like within the individual data center, you're going to have a ton of TPUs that can very quickly communicate with each other, but those TPUs, if they wanted to communicate with a different data center, a different TPU in a different data center, that would be a much longer and more costly communication. So you have this kind of like islands of devices. The approach is a variant of federated averaging. So this is a reference to federated learning, which was kind of an older idea. Federated learning is like an older term now, but it basically was this idea that you could do training kind of on device, right? So kind of what I remember from federated learning was like, okay, rather than training on a GPU, maybe you can get a cell phone to basically train on the data that is on that cell phone and then communicate back the weight changes, right? The little weight deltas. But I haven't heard this term in very long, maybe not, probably this year. So very long is relative, but it is within that sphere, I guess, where the number of inner steps is large. The inner optimizer is Atom W, and the outer optimizer is Nesterov momentum. So we're going to get into that later. I think it's probably better we leave that door closed. The widely used C4 dataset, this is the common crawl dataset. We show that dloco on 8 workers performs as well as fully synchronous optimization while communicating 500 times less. Yeah, so I mean, like I said, this doesn't really mean anything because it's like you're not really comparing to anybody else. So it's like it's faster than what they were doing previously, but there's nobody else that has the same exact setup, so there's basically no one to compare this work to. dloco exhibits great robustness to the data distribution of each worker. It is also robust to resources becoming unavailable over time and vice versa. This paper isn't as fault tolerant and robust to a changing and kind of morphing compute mesh or compute set as this paper. So this paper is much more robust to constantly changing the devices and devices coming offline, going back online. But this one does have some amount of fault tolerance-ness. It can seamlessly leverage resources that become available during training. Let me just close this door. I'll be back 1 second. All right, sorry, my kid is screaming in the background. It's very hard to concentrate. All right. I highlighted a couple things in the introductions here, and then we'll go through that first. So we're here on the Google paper. So in the Google paper, they have this introduction section, and I think there's a couple important things here to call out. So performance has scaled with model size. Practitioners train increasingly larger models on increasingly larger data, right? This isn't really news if you've been in the machine learning world, but just in case you're new, the bigger the model and the more data that you train it on and the longer that you train it for, the better the model's going to be, right? It's not always true for every single case, right? There's still a lot of improvement to be gained by improving the way that you train or improving the model architecture or maybe cleaning your data set and improving that data set. But as a general kind of rule, the bigger you make something, the longer you train it for, and the bigger the data set is, the better it's going to train. So basically, in any organization that is trying to push the state-of-the-art of machine learning and AI, they're trying to figure out ways to make everything bigger, right? 10x the scale. So you're not going to be able to just keep making bigger and bigger GPUs. So now it's all about distributed training, distributed inference, right? Can you use many, many different GPUs to do a bigger model, a bigger train on a bigger data set, train for longer, and so on. Okay. Interconnected with high bandwidth cables to minimize latency. So here this is referring to the fact that, and we're going to take a little detour here. So this is the detour. Maybe, actually, I want to start here. So this is, whenever people talk about data centers, this is what they're talking about, right? So this is some, I don't even know what this is, but this is like some random guy. I like this picture because it has a guy for scale, right? And this is what a large cluster looks like, right? You have this room, and in these room, you have these kind of cabinets, right? And then inside each of those cabinets, you have these kind of drawers, right? Or slots. And then each of these slots is a computer. And inside each of those computers, you basically usually have 8 GPUs. So you can think of this as basically the top-down view of one of the drawers inside one of these cabinets, inside one of these rooms, inside this data center. So the way that those are actually connected is actually kind of usually like this. So within each of these is basically, you can think of this as one computer, which is roughly one kind of server, which is basically one of these drawers. But within that, you're going to have a single CPU, right, that can communicate to the main memory. This is usually called the RAM, the RAM, the random access memory. And then that CPU is usually connected to a bunch of different GPUs, right? So you can see here how there's multiple GPUs connected to basically this one server. And each of those GPUs has separate GPU memory. This is sometimes called the VRAM, VRAM. So RAM is this one, and then VRAM is this one. So performing any calculation where all of the information, when you're performing the actual calculation, you're actually performing it on the GPU, right? So if everything you need to perform that calculation is inside this GPU VRAM, it's going to be very quick. If you have most of what you need in the GPU VRAM, but then you also have to grab some stuff here from the RAM, it's going to be a little bit slower, right? Because now the GPU is going to have to sit there and it's going to have to wait for the CPU to come, and it's going to grab some stuff from here and then go back up and put it in the GPU VRAM, and then you're going to calculate. So as soon as you have to go outside of anything like this, it's going to take time, right? And now imagine you're doing a distributed training or distributed inference where now you not only have to go here to the RAM, which is at least on the same server, but you have to wait for something that goes through the network, right? So now you have the network here, think about like literally like a little Ethernet cable that's plugged in, right? So within a data center, right, the interconnects that connect these little servers are pretty fast. But then there's a level on top of that, right? So now think about, okay, now the network speed between these little servers within the same data center might be fast, but now what about the network speed between data centers, right? That's going to be slower. So this is kind of I don't know, just some stuff to think about. Okay, let's go back to here. Passage of gradients, parameters, and intermediate states at each optimization step. So here, this is the 3 main things that you're going to be communicating between these different GPUs here, right? So you're going to be communicating the gradients, which is basically the change in the weights, right? How much you're going to change each of the little 70 billion parameters in a Llama 2. Those are going to be the gradients. The parameters, which is going to be the actual weights or parameters of the neural net. And then the intermediate states, which is going to be like any intermediate values, right? Within an individual model, right? The model is composed of a bunch of usually repeating transformer blocks. And then each of those transformer blocks, you could basically slice right in between, and that little state in between is called the intermediate state, right? And sometimes the way that they split the compute over a bunch of GPUs like this, they'll be doing something called model parallelism, where they're maybe this GPU is calculating the first transformer block, this GPU is here calculating the second transformer block, and this GPU here is calculating the third transformer block, right? So you can see how that can introduce some latency, some slowness, right? Because this GPU here, if it's calculating the second transformer block, it needs the input or the output of the first transformer block. So it needs to wait for this GPU to calculate the first transformer block, and then this GPU will say, okay, I calculated the first feed forward through the first transformer block, and then I'm going to send that information over here through the network, up through here, through the PCIe back to this GPU here. So this waiting can basically be kryptonite here, and I have an example to show you how this can really affect situation. So here you have 4 devices. So assume that device 0, device 1, device 2, device 3, these are different GPUs that are each computing a different part of the model. So here you have a type of model parallelism, which means that here F0, F1, F2, F3, this refers to, let's just say you have this imaginary transformer model that has 4 blocks, right? 4 repeating transformer blocks. And you're going to give each GPU is going to calculate 1 transformer block. So you can see here how you have this problem where the second GPU here has to wait for the first GPU to finish before it can even start doing its job. And then here's the third GPU, and then the fourth GPU. And then this B here, F stands for feed forward, which means forward, which is going to be kind of what you're doing in inference. But even when you're training, you need to do feed forward steps, right? Because you need to actually calculate what the value is going to be for you to do the loss function and then back propagate. I should do it this way. But here during training, right, you're going to have feed forward and then you're going to have back propagating steps. So you can see how the same thing happens here, right? Where if you're back propagating, you also need to wait for the parts that are in the model ahead of you to go backwards. So all this time here is dead time, right? This is all this like empty space here is time when this GPU is just sitting idly. And you don't want to have any idle GPU time, right? Because it basically means that your GPU is sitting there not doing anything, just wasting energy, just wasting time. So this is an issue, right? And we'll go into what this is later because this is a little bit more complicated. But I kind of wanted to show you guys a little bit, introduce kind of this problem of data centers and communication and a little bit of model parallelism. So let's go back here. Okay. We take inspiration from federated learning. Again, this is kind of what people used to call this idea, but I feel like federated learning is kind of old, which is why people don't reference it as much. There are K workers. K workers, each GPU is going to be a worker, I guess, or here each worker has a bunch of devices. Workers perform some amount of work locally and then exchange gradients every H steps. Okay. Devices within an island need to be homogeneous. Different islands can operate with different devices types. Okay, so here what they're saying is that devices within an island need to be homogeneous. What they're saying is that within an individual island, let's just say one island is one of these servers, all the devices on that server need to be the same. So see, if you look at this image here, so this is some image of a server in some NVIDIA data center, notice how every single one of these GPUs is the same. RTX 4000, RTX 4000, RTX 4000, RTX. So all the devices on this node are homogeneous. But that's a very strong assumption, right? Because you can really only make that assumption if you're Google and you're dealing with large data centers that have this homogeneous devices on every single island. But that's not going to be the case if you're doing open source work. In open source work, you're going to have a huge mishmash of different GPUs. You might even have different devices on the same node, right? So like if you have a computer and you have 2 GPUs on that computer and those 2 GPUs are different GPUs, that's going to be a kind of a deal breaker for this type of situation. In the question from the audience here, in the Gemini paper, they mentioned that it was trained using more than one cluster at the same time. Yeah, so this DiLoco distributed low communication training is probably what they used to train Gemini because, as XR7RKE is saying here, they mentioned that they trained it over multiple data centers, which means that this is probably what they did. Okay. On the C4 dataset, interesting note here, the Common Crawl dataset, this C4 dataset, you see this Rafael? This is the same guy here. So, Colin Rafael. Or I think it's Raffle, I'm not exactly sure. But interesting, the amount of kind of, it's all the same people just pushing the same papers. DiLoco can achieve even better performance than a fully synchronous model while communicating 500 times less. DiLoco is capable of effectively utilizing several islands of devices, robustness to island failure, and nicely leveraging islands whenever they become available. Okay, so you have to be robust to one specific island just dying, and then you don't want to have a situation where, for example here, let's say that your GPU this GPU here, let's say it died halfway through, and then in this case, with naive model parallelism, you would just be done, right? This is nothing you can do because this GPU would just sit there and just wait for this GPU to reboot and recalculate. So like if you have this kind of chain of dependence where you need 100% on 100% or 0% of error rate, right? You need all of these devices to be online for this to actually work. So fault tolerance is quite important because you can't usually guarantee that. In a real system, you're going to have GPUs that randomly die. You're going to have specific server boxes that die. You're going to have data centers which get disconnected. You're going to have all these different types of errors, and you need to be robust to that. Okay. So that was the introduction section, and now this is going to be the DiLoco, the method section, which is basically going to be explaining exactly what their process is. Okay, I think before we go into this, let's go into this paper, because I think this paper does a good job of describing some of the main parts here. The background section of this paper is quite good. But first, let's go over this shit here that I highlighted. Okay. Figure 1, a high-level overview of our system design. Servers store pre-trained large language model layers and temporarily hold attention caches for inferencing. So here they're talking about the KV caches, which are an important part of inference, because when you're doing inference with a transformer, usually, right, the transformer encodes the entire prompt and then autoregressively decodes token by token. So having the encoded prompt in that KV cache, which is also it's going to be very important for speed, so that you don't basically need to recalculate that constantly. The clients hold embedding layers and learn prompt adapters. This server client, they're going to describe this later, so that's an abstraction that they create here. But mostly here, what you are interested in seeing is that they have Bloom, which is a specific type of model. So Bloom is like a very large transformer-based language model. You see here how it has part 1 out of 3, part 2 out of 3, and part 3 out of 3. So this is, you could think of it like a model parallelism or pipeline parallelism, right, where basically they're splitting up the model over a variety of different devices. Okay, so here you have some GPUs, and then here you have an example of some server racks. So this little diagram shows a server rack. This diagram shows some GPUs. Communicating activations over a slow network can be faster than swapping layers from local RAM or SSD. Okay, so here, what are they saying? They're saying that sometimes communicating activations over a slow network, so let's say that this GPU was performing the first transformer block, and this GPU here is performing the second transformer block. Sometimes communicating the activation, so what comes out, the output of that first transformer block, and then just sending it over here through this PCIe, through this network, up through this network, up through this PCIe, and into that. Sometimes that is faster than, let's say, this GPU here. What if it had to do the first transformer block and the second transformer block? So if it had to do the first transformer block, it would calculate the first transformer block. Then it would have to store that here in the RAM. Then you would have to load the second transformer block, then send back the activation that you got in the first one, get the activations for the second one, and put it back into the RAM. So what they're saying here is that sometimes communication is actually faster than swapping layers out from your RAM, or even worse than your RAM, your solid state disk. So they don't have a solid state disk here, but imagine that there's another arrow that comes out here and then goes to a little hard drive over here, right? So that would be even slower. So they're talking about CPU RAM access being slow. Like imagine CPU SSD access. That would be unbelievably slow. Okay, it should be possible to run LLMs cost effectively by pulling together commodity hardware over the internet. We formulate a novel algorithm for fault-tolerant distributed autoregressive inference of very large models. So fault-tolerant there, referring to the fact that it needs to be tolerant to some of these GPUs dying halfway through, adding more GPUs randomly halfway through, and so on. Autoregressive refers to the fact that transformers, especially the decoder part of the transformer, is autoregressively performing inference. So for the transformer to predict the next token, it needs the previous token, right? And then for the transformer to predict the next token after that token, it needs the token that it's currently predicting. So every single step of inference, it's basically auto-regressing. It's regressing on its own output. So that's what the autoregressive inference refers to. And then the very large models just refers to large language models. Okay. Using dual attention caches, this is this KV cache concept, right, where you're storing or caching. Caching comes from the French word cacher, which means to hide, and it's used in computer science to denote whenever you're kind of like intermediately storing some value that you're going to need later, right? So you don't need it right now. You need that information later, so you're just kind of storing it in some memory. It can either be cached somewhere here. There's different, even within the GPU, there's different caches of memory. Within the RAM, there's different levels of memory. So there's a bunch of different places in a GPU where you can kind of store that information, or in a computer where you can store that. Allow participants to add or remove the devices at any point, making optimal use of GPU idle time. Okay, so the bulleted points here at the end of the introduction basically summarize all the work, or all the important contributions here. This is the first algorithm that can inference LLMs with 50 billion parameters. Petals is the name of this system, and then they benchmark it on Llama 2, and then the Bloom 176B model, which is this model here, Bloom. Okay. Background. Okay, so this background section, this is the reason why we were here, because I think this is a nice little background section that introduces a couple important concepts here. Okay, model parallelism, tensor parallelism, pipeline parallelism, and data parallelism. Those are different types of parallelism. So model parallelism assigns each device to hold a subset of the model parameters, run a subset of computations, and communicate the output activation. So I have this diagram here. So how the model weights are split over cores. So cores here, you could think of this as basically GPU. So whenever you see this core, or each of these little squares here is one GPU. So when you're splitting, or when you're using model parallelism, right, think about this blue curved square representing all the different weights that you need for one model. So if this blue curved square was Llama 2 70B, all the blue weights here are basically all the different parts, all the different little transformer blocks inside that Llama 2 70B. When you're doing model parallelism, what you're doing is you're splitting that Llama 70B over a bunch of different GPUs, right? So here you have a 4x4 grid of GPUs, so you have 16 different GPUs. Each GPU is going to have a little different part. Maybe this one here has the first transformer block, this one here has the second transformer block, and so on, right? So this is model parallelism, where you split the model over multiple GPUs, multiple cores, multiple devices. Data parallelism is when you're splitting the data, right? So what do they refer to by the data here? Whenever you're training, right, you're training with batches of data. So you're basically feeding a batch of data, a batch of training data into the model. You're calculating the loss function, and then you're back propagating that loss to get the actual gradients, to get the actual deltas that you need to change the weights of that little part of the model, right? So in data parallelism, you're basically, think of it like you're taking your data and you're splitting it, and then each individual GPU is calculating the full model, but with a little piece of the data, right? Versus in model parallelism, each individual GPU only has a little piece of the model, and it might have the full data, but it might not, right? So these things are not mutually exclusive. You can have both of them. You can have model and data parallelism. You can have model parallelism only. You can have data parallelism only. And then this diagram is even more complicated because expert parallelism is also a thing. Expert parallelism comes from a mixture of experts model. So everybody knows about these mixture of experts. You might have heard about the Mistral MOE that was pretty popular here during the NeurIPS conference. And in a MOE model, within the model, there's this notion of basically little experts, and then you route into specific experts. And in expert parallelism, the different cores or the different devices or the different GPUs each have a different expert, right? So these are all just different terms that all describe the same basic idea of like splitting up information into different GPUs. That's largely all that you kind of really need to visualize in your head. Okay. But depending on how you split it, you're going to have to do different types of communication, right? and some of that communication might be really bad or not bad, right? Tensor parallelism assigns each device to compute a subset of each model layer. Okay, so maybe rather than splitting the model like one transformer block on two different GPUs, maybe what you do is you actually say, okay, well, the first half of this transformer block and the second half of this transformer block, like think about the width, right? Like if you have a fully connected little neural net, you have these layers of neurons. Rather than saying, okay, well, this GPU is going to get the layer 1 and then this other GPU is going to get layer 2, what if instead you did tensor parallelism and then you're basically saying, okay, well, this first GPU is going to get this kind of first half of layer 1 and the second half of layer 2 and this first half of layer 2, and then this second GPU is going to get the second half of layer 1 and the second half of layer 2, right? So again, fundamentally it's this same thing of just splitting this pipeline across a bunch of different GPUs. Okay. Each device performs a symmetric computation applied to a different slice of model weights, which makes tensor parallelism compatible with MPI-based communication. Thus, the main performance overhead of this strategy comes from an all-to-all communication after each layer. So, all-to-all communication, here's one way to think about it. I think this is what I want. Okay. So, if you have a bunch of these little nodes, right? The communication, there's different types of communication. So one type of communication is broadcasting, where I'm a little GPU and I computed something, and now I need to send that to a bunch of other GPUs that might want to use that, right? So in a model parallelism system, I might have computed the output of transformer block 1, and now I have a bunch of other little GPUs that want the output of that, and I'm going to broadcast that across, right? So I'm going to basically send that information to a bunch of other GPUs. A different type of operation might be something like a gather. In a gather, right, I'm a little GPU and I'm calculating the second transformer block. I need to have all the activations for the first, or I need to have basically what comes out of the first transformer block, but maybe I'm in a tensor parallelism kind of world, and what comes out of the first transformer block is actually being calculated by 4 other GPUs. So now I need to wait for each of these 4 GPUs to finish to give me each of their little chunks in order for me to do my calculation. So this is this kind of gather, right, where you're kind of waiting for all this information to come before you can do your own thing. All reduce is kind of like, you could think of it like kind of the combination of all of those, which is basically every GPU is calculating something, but in order to do the next thing, they need to basically get all the information from all the other ones. So you're basically, this all-to-all communication is kind of the worst, right? But in a lot of these situations, you need it, which is basically all reduce, or what the way that they described it here, all-to-all. That's going to be the most heavy because it basically says that every single GPU is going to have to communicate something with every single other GPU, right? And that's great if all your GPUs are all like right next to each other in a data center, and they're connected with some ridiculous local area network that has really, really fast interconnect speed. But all-to-all is going to be really bad if even just one of your GPUs is sitting on some computer in the middle of Mongolia with a terrible internet speed, right? So this all-to-all communication is very sensitive to basically the weakest link in your distributed compute system. Okay. Pipeline parallelism reduces the communication overhead by assigning each device with one or several full layers. Okay, so now a different type of parallelism, right? Where you're basically now splitting within one GPU, it has several full layers of that. Each stage applies a subset of layers and then sends the output of the last layer to the next stage. The pipeline must process multiple microbatches per step, allowing each stage to run in parallel or on a different batch of inputs. And that's kind of what's going on here, right? So here, F01, F0, I'm not exactly sure what's going on here, but you can see how this F10 only needs the output of this F00 to start working. So what you can do is, rather than doing all of it here and then having to basically this one sits idle until this one entirely finishes, you can have this one start working on only just the first part of what's coming out of here, right? This is a feed forward process, right? So you can see how if you split it up just a little bit more and you communicate a little bit sooner, like, sure, you're going to have to communicate more. So you can see here the amount of communication here is you're communicating here, you're communicating here, you're communicating here. So you only have to communicate 4 times here. Here, there's a lot more communication, right? You're communicating here and here and here and here and here. So there's more communication. But if your communication is fast, now this is actually faster overall because you don't have as much idle time, right? So there's always this trade-off of like, if communication speed is fast, then certain types of parallelism are better. If communication speed is slow, certain other types of parallelism are better. If your devices are all the same, certain types of parallelism are better. If your devices are heterogeneous, then other types of parallelism are better. So this is kind of what I mean, that there really isn't an optimal strategy here, right? So like one thing that I got taught in school was, if my advisor taught me this, he said, anytime someone says the word optimal, ask them the question, optimal with respect to what, right? So in this case, the with respect to what, there's such a huge different types of with respect to what, that optimal doesn't really mean anything. It just means optimal with respect to this particular constrained, contrived situation that we've created. Damn, I feel like I'm not saying great things. You guys need to interrupt me with questions because I kind of go on these rants and I have no idea if people are listening or no one gives a shit or what's going on. I need more coffee. That's what needs to be happening. All right. Both of these strategies are actively used. Real-world distributed training systems usually combine multiple forms of parallelism depending on the hardware and the network type. Tensor parallelism is typically used within a single multi-GPU server or closely interconnected TPU cores. TPU is basically just Google's GPU. It stands for Tensor Processing Unit. But largely this paragraph is just kind of repeating what I've been trying to say in worse words, which is that the types of parallelism are going to depend on what you're working with, right? So open source company like this that's working with a huge distributed heterogeneous devices that are communicating at different speeds. So even within here, right, there's going to be different communication speeds between these different devices versus here in Google, every single TPU inside this island, as they call it, is exactly the same. And the interconnect speed between all the TPUs in this little island here, which is the American data center, is extremely fast, right? So different types of parallelism are going to work. So maybe here we can look at the Google one, for example. Here they have 4 data centers here. So you can imagine a data center in the UK using A100s, a data center in Japan using TPU v5, a data center in France using V100. These are all different types of GPUs. And I wonder if this is actually true, right? So like, do you think that the Google cluster in England uses A100s and then the Google cluster in America uses TPU v4s? Or do you think this is just made up? I don't know, right? I'd be curious. Like, I feel like they wouldn't tell you that, right? It'd be weird if Google literally like leaked the exact hardware that they were using in each of their data centers in a paper, but I don't know, that'd be kind of cool. Okay. Let's go back to here. Offloading. Okay, so offloading. What is offloading? Parameter offloading relegates model parameters from accelerator memory to a slower but cheaper storage, typically RAM or SSD. So model parameters from accelerator memory. So basically right here, right, your accelerator memory is your VRAM, and it's offloading it to here, the RAM or the main memory, or the SSD, which is, you can think of it like an extra little arrow going here into an even slower memory. So offloading is this idea that, okay, maybe you can't load the entire model on your GPU VRAM, but you can load one part of it. And then if you want to load a different part of it, now you're going to have to go back to the RAM, load that second part of it, run that second part of it, and then go back to the RAM, load the third part of it, and so on, right? But the problem is that having to unload and load through all the model parameters is very time consuming. Okay, blah, blah, blah. Using pre-trained a method. Okay, so now we finally get to the method section of this paper. The inference workload typically consists of encoding an input text and then generating tokens autoregressively. So this is the large language model typical workload, right, where you're encoding the entire prompt, and then, right, the entire prompt can be encoded at the same time because it's just self-attention. But then when you decode that prompt in order to autoregressively predict tokens, you're going to need to do this cross attention with the last token. So you can't do the cross attention all at the same time because it's going to have to pay attention to its own output. So you're going to have to wait until it actually predicts the next token to then do the next step. So that's kind of I feel like I explained this a million times, so I'm sorry if I explain it yet once more. Fine-tuning requires updating either all of the model's parameters or a small set of trainable weights. So the first type of fine-tuning that they're referring to here, where you're updating all of the model parameters, that I feel like nobody does that anymore, right? So the type of fine-tuning that people do nowadays is usually through adapters such as LoRa's, and in that case, right, you're actually keeping most of the model frozen, and you're really only training these little LoRa's, and that means that the fine-tuning workload is actually very similar to the inference workload, right? So if you're fine-tuning a language model using a LoRa, right, what does the workload look like when you're training, right? Well, what you're doing is you feed your training data through the actual frozen language model, and then the back propagation is only being done for that little LoRa, which means that from the point of view of your pre-trained frozen language model, all it's doing is it's just performing inference with a batch of data, right? It doesn't care whether it's actual real data or whether it's training data, right? So for a variety of reasons, these adapters or LoRa's are basically the only way anybody does fine-tuning nowadays, and because of the way that works, the fine-tuning workload from the point of view of the actual pre-trained frozen language model is really, really similar to just an inference workload. Okay, here they have some other kind of more niche things here. We found that inference is more challenging than fine-tuning. Okay, blah, blah, blah. Performance bottlenecks. Okay. Unlike training, autoregressive LLM inference cannot be done with a single pass through the model. Instead, the model needs to process one token at a time, pass it through the entire model, and then generate the next token and repeat the process. Question from Ed here. Can you use Diloco with JAX? Because TPU can only be used on JAX, right? Yes, you can. Diloco is irrespective of the model framework. So JAX is a framework, which is something like a PyTorch or a TensorFlow, right? It's like the actual compute language that you're using to define your compute graph, right? But Diloco is not specific to a specific type of framework, right? You could implement Diloco in any Turing complete language, right? But I bet you that Diloco was written in JAX because the people at Google who do this type of training are using JAX. TPU can only be used on JAX. I want to say yes, but I'm not 100% sure. I'm pretty sure. Can you TPU PyTorch? Yeah, you can create PyTorch code that runs on a TPU, so it's not exclusive. Is there another format to be able to combine GPU and TPU machine output? So the way that this Hugging Face setup is run, some of these can be TPUs, right? So there's nothing here that requires all of these to be running PyTorch or all of these to be running some specific, like some of these could be NVIDIA GPUs, some of these could be TPUs, some of these could be like some other weird type of GPU, as long as they're basically able to communicate the activations or the gradients, which are just a bunch of numbers. It's just like a matrix of numbers. As long as you can communicate that, then it's completely fine. So hopefully that answers your question, Ed. But let me know if you want a better answer. Okay. in the case of model parallelism, training an N3 layer model needs O of N communication rounds, while generating the same sequence needs O N of T rounds, making it more susceptible to network latency. Okay, so for those of you that might not be super familiar with this, so this is called Big O notation. And Big O notation is a way of basically communicating how fast a particular algorithm needs to run, but not necessarily speed. It can also be memory, right? So there's some algorithms are scale differently with the length of the input, right? So O of N means that however much this N is, so if you have a model that has one layer, it's going to, the speed of that is going to, or not the speed of that, the amount of communication you're going to need is basically O of 1. If you have a 3-layer model, now you need O of 3. So you see how, like, as you increase the number of layers, right, the amount of communication that you need is also increasing linearly with that, right? So that's what this O of N means, that it's linear scaling, right? So if this was an N squared, right, then you could see how as you increase the amount of layers, the amount of communication would increase quadratically, and the total amount of communication would start to balloon, right? So, wow, I'm so bad at explaining these things. Okay. What is going on here? Here they're calling it running time complexity in terms of big O, and then input size N. So some algorithms scale linearly, like this O of N. So this is the total amount of compute that you basically need, right? Or the running time complexity. So if your algorithm scales with O of N, or even better than that, O log of N, then you can keep increasing the size, and it's fine, right? It's not going to be that much worse to calculate it for 1,000 layers versus 1 layer, right? But if your algorithm is O n log n, which is quite common, or O n squared, you can see how it starts to get more and more intense, right? If you're O n squared, the difference between 1 layer and 1,000 layers is huge, right? And a good example of this is in transformers, the attention block is O of n squared, which means that the length of the sequence is quite important, right? And you start even just increasing that sequence a little bit, doubling the size of the sequence, you start quadratically increasing the total amount of compute that you need. So hopefully that world's worst explanation of Big O notation is enough for you guys to understand why O of N is really what you want to be shooting for versus O of T to the third here, right? That's terrible. It was clear. I feel like I'm like really bad at explaining. I think I'm just rusty, you know? During an inference, okay. Also takes O of N. The other problem of autoregressive generation is dealing with attentions for past tokens. During an inference step T, each layer needs to attend to T-1 previous attention keys and values. So this is the autoregressive part, right? Existing inference algorithms store past entries in accelerator memory. So here they're referring to the fact that a lot of the caches, the KV cache is usually often stored inside the VRAM, right? Which is great because it means that you don't need to go to the RAM to go grab that. And here, for example, they give you a nice kind of a example. So for GPT-3, you have 2048 token sequence, right? You're storing that at half precision, which means that usually rather than float 16, maybe float 8, right? So the data type of each individual number is going to be how much actual raw bytes or raw memory you're using. So the precision of the numbers that you're storing is actually quite important as well. And because this is a Tim Detmer's paper, you can bet your ass that they're going to be doing half precision and more fancy quantization techniques, which is just reducing the total amount of memory that each individual little number takes, right? But for a 2048 token sequence with GPT-3, the KV cache is 9.6 gigabytes of GPU. Actually, it's not even the KV cache. It's the entire sequence is 9.6 gigabytes of GPU memory. So it takes quite a lot of GPU memory. That's like half the GPU memory that I even have on this computer just to store the entire context. Offloading these cache values faces the same problem as of offloading in general. So here they're saying that much like any other random blob of numbers, you can always do the same trick of offloading where you just kind of store it here in the main memory rather than having to store it here. But as soon as you do that, that means that you're going to have to kind of go back and forth and back and forth and back and forth. And that back and forth is can absolutely shoot you in the foot. Recompute all the tokens in every inference step, but that's a terrible solution. Parameter offloading can still be efficient when generating a large amount of short sequences in bulk, but that's not really realistic. Hence, we explore a new solution based on pipeline parallelism. Okay. Distributed generation with fault tolerance. So self-conscious today. Yeah, sometimes I feel like I don't explain things clearly, right? It's like I really want to explain things clearly, but I just end up going on these rants where it's like, you know, I'm self-aware of it, right? I'm like metacognitively analyzing my own output, and I'm just like, wow, this is a terrible ass explanation, right? But I don't know. I'm just trying my best, guys. You know, maybe we're just all here to hang out. Inferencing LLMs in a fleet of unreliably geographically distributed devices connected over the internet. So maybe here's a meta point, right? So a lot of people say, okay, well, a giant AI system that's going to take over the world like a Skynet, like you could always just turn off the GPUs, right? But that's not actually what it's going to look like in the future, right? Once you get to a point where you have, for example, like Bitcoin, right? Like think about something like Bitcoin. Bitcoin, you can't kill Bitcoin because there's too many unreliable, geographically distributed devices connected over the internet, right? In order to kill Bitcoin, you would have to turn off every single GPU, and you're never going to turn it off, right? There's always going to be at least one. There's like some random person with a Starlink connection in Tibet, in a mountain, like with a Bitcoin node sitting there, and unless you were able to shut off every single node, Bitcoin would keep going, right? So maybe in the future we'll have a very similar type of situation with a giant decentralized AI that is running on a huge cluster of nodes that are all over the internet, and it's impossible to shut off that AI because no one has control over every single node, right? Even the US, like, maybe they can shut off all the nodes in any country that is friendly to the US, but then there's always going to be at least one random ass like country, some random person in Kazakhstan who's still running some devices, and the AI will be able to live in those devices. So I don't know. I think that's a good thing because it basically means that it's censorship resistant, but I think it's just a reality, right? Okay. A client holds input and output embeddings, and a server is a GPU-enabled node holding a set of consecutive transformer blocks and processing requests from client nodes. So here, this is server-client. Server-client has a billion different definitions. It's generally like a high-level idea is that the client is your, for example, your computer, and then the server is the cloud computer, and the server serves you, for example, a web page, right? So like whenever you are going on a web page, there's a server that is serving you that web page. But here they're kind of reusing that terminology, and in this particular paper, a client is the node that actually you are running, right? And you are the person that wants the inference, right? Versus the server is a node that is performing some computation for you. So in this case, the server is basically hosting a set of consecutive transformer blocks. So this is a type of pipeline parallelism, right? Where in the Llama 2 model, right, however many consecutive transformer blocks there are, you're going to have one GPU that has maybe just the transformer blocks 2, and then transformer block 3, and then transformer block 4. And all it does is it sits there, and you say, hey, here's the output of transformer block 1, and I want you to feed it through your 3 little blocks and then give me back that, right? So the client has all the information of the actual input and output, right? What's going in to each individual transformer block and what it needs at the out, but the server is just sitting there doing the same computation over and over again, and that computation is just a specific brick of the full pipeline. Autoregressive generation requires many sequential communication counts, making it sensitive to network latency, right? So this entire system is going to be very sensitive to network latency because of this situation, right? You're going to have to wait, like, if you are the client and you say, okay, here, I'm sending this out. I want this server to communicate the next 3 blocks, or to calculate the next 3 blocks for me. It's going to have to sit there and wait for that server to do that and then receive that information back, right? So you're sitting there, and if this communication takes forever, right? Like, let's say this F0 is some guy sitting in Tibet, and then this F1 is someone in like Belize. Right now, you have to wait for communicating all those intermediate activations over the satellite internet from Tibet to Belize, back over the internet back to Tibet. So network latency can be kind of a huge issue here. If a remote server shuts down, any cached attention keys stored on that server will be lost with it. So here they're talking about the failure case, right? Restarting might be enough. However, running 50B models, in turn, recomputing past attention caches requires communicating past tokens on every communication round, resulting in more total data transferred. So pretty bad scaling there. O of n t squared. Generally, the way these big O notations work is you would drop this n, right? So like, if, for example, you had a big O notation of 3n squared, you would just write that as O of n squared, because the 3 doesn't really matter, right? The dominant term in that big O notation, the one that's going to take the most time, is that n squared. So here, O n times t squared, the t squared is kind of really the dominant term here, right? Because the sequence length t is going to be much bigger than this n, so this n is going to be whatever, like something like 8, and this t might be something like 2048. Okay. We maintain 2 types of caches. Server-side cache holds past attention keys and values for their layers, and then client-side cache holds past inputs sent to the given pipeline stage. So they're kind of doing a little bit of duplicate caching, but this kind of like duplicate caching where the client is storing some amount of, caching some amount of stuff, and then the server is caching some amount of stuff, that will make it more robust to these failure situations where either the client dies or the server dies, and so on. For every pipeline stage, the client maintains a heap or a priority queue of servers that hold this stage and may hold additional stages. A queue is a very simple type of data structure in computer science, right, where it's basically a first in, first out. So it's like a queue, it's like a line at like a grocery store, right, where the first person that waits is going to be the first person that gets out. But a priority queue is a queue where each individual person in that line at the checkout also has like a priority, which basically says that the person with the top priority gets first, even if they came in last, right? So like maybe you're at a grocery store and someone with like a wheelchair comes up. Even if they're the last person in that line, because they're in the wheelchair, they have a higher priority, so they're going to get served first, right? So that's a priority queue. The client is maintaining a priority queue of servers. So the client, right, which has the actual activations, and it's only sending those to the servers, which are running maybe transformer blocks 2, 3, and 4, right, consecutive transformer blocks. The client has a list. It has like a little list in its memory where it says, okay, here are the good servers. So here are the servers that can communicate or that can do each of these different pipeline stages for me, and I also know the network latency between that. So it's keeping a little short list, a little priority queue of like, hey, this server can do these calculations for me, and this server is faster than this other server, which would do the same calculations for me, but maybe that server is somewhere in Tibet, and the network latency is much higher. So it's constantly maintaining this priority queue of like which servers are worth sending information to because they're faster, because I'm connected to them through less crap usually. And the problem, so this is great, right, if you're in this situation here where you have this heterogeneous different interconnect speed situation, right? But there's overhead in doing that, right? With any of these things, if you have to maintain this heap or priority queue of servers, you're going to have to spend CPU clock and to basically keep that, and you're going to have to spend a little bit of RAM to also maintain that, right? So if you don't need to do that, in the case of, for example, this Google paper, then you shouldn't need to do that, right? So like, I don't know, something to think about there, where like just keeping track of this is extra compute that if you don't need to do it because you already know exactly the all of these are connected much faster, right? You don't need to have this, right? This little TPU v4, it's connected to all the other little TPU v4s inside this data center. It doesn't need to have a list of the TPUs sorted by interconnect speed because they're all interconnected together and the interconnect speed is largely the same between them. Okay. Once the server obtains output activations, it sends them both to the client and the subsequent stage. Shortest path routing. Computation time determined by the server's compute throughput and the network latency. So it's not a priority queue of just the latency, it's also a priority queue of how fast individual servers are. So there's obviously going to be some servers that are more beefy GPUs and they can calculate an individual part, a little part of that pipe faster than maybe a different server that is also calculating that same part of that pipeline, but is on a shittier GPU and therefore it does it slower. So there's going to be, you have to account for both things, right? Because you might want to communicate with a shittier server that is closer to you because of the network speed rather than a very fast server that is much further away from you. Servers measure their own compute throughput and share this information. The client measures the network latency between them and a given server by pinging the candidate servers during routing. See that? So this is something that you can also take advantage of, right? So in this situation here, right? So here we're talking about multiple GPUs, each computing a different part of the model or a different part of the pipeline. And here, right, they're waiting because they're idling because they need to wait for the input from some other model, right? Or some other part of the pipeline. But what if instead of just completely idling, you got them to do something? So during this time here when they're waiting, they're doing something useful. And what that useful thing they're doing is they're pinging other servers and then maintaining this little list of what the good servers are, how long each server takes, and the latency between the servers. So I like this idea of like, hey, while you're idling, right, while you're sitting there and you're not doing anything, you might as well use that time to do something useful. And the useful thing that you could be doing is maintaining this graph, right, which is a bunch of little nodes with edges where you're basically saying, okay, here's my current available servers, here's the little speed of each of them, here's the interconnect between all of them, so I can constantly use some kind of path planning here, D star light, which is kind of like an A star variant, where I can basically figure out, okay, I already know which servers I'm going to call for each of the different parts of my pipeline that I need for this particular inference request or inference workload. Okay. Automatic load balancing. In order to run inferences or fine-tuning, each server needs to be assigned into a pipeline stage when reassigned if other servers join or leave the network. Servers may have different compute throughput, network bandwidth, and geographical locations. Servers periodically run a load balancing procedure and switch to new blocks if necessary. Okay, so the servers themselves, right, if they know, because you're constantly adding nodes and removing nodes from this larger computational mesh, it might be the case that you start realizing that, hey, actually we have too many servers that are serving this particular part of the pipeline and not enough servers that are serving this other part of the pipeline. So you do this load balancing that says, okay, well, actually, let's switch some of the servers that are serving this particular part of the pipeline to using this other particular part of serving this other particular part of the pipeline so that the overall total system throughput is maximized, right? Each server periodically announces its blocks and empirically measures throughput to a distributed hash table. When a new server joins, it uses this information to identify a contiguous interval of blocks that would increase the total system throughput the most. Okay, so you can see how there's a lot of load balancing and path routing and maintaining these heaps of different servers and different ways of doing it. So there's a lot of overhead here, right? Like you're spending a lot of your compute like constantly basically doing this load balancing, maintaining this distributed hash table of like what the best servers are for each of the different parts, maybe shutting down a server, respinning it up as a different part of the pipeline. So normally that amount of overhead should raise kind of a red flag, but if you're going to be using this type of system where you have all these different nodes everywhere, you need that overhead, right? And it's not only just, you're not just doing that for fun, you're doing that because you need to identify the fastest possible path through that. Okay, let's switch to the Google paper here. Let me sip some more coffee and then we'll go. Okay. All right. Thanks for supporting me, guys. Okay, so this Hugging Face paper has we've largely been talking about kind of an inference-like workload, right? So in this workload, right, or in this workload, it's mostly about how do you perform inference, specifically a type of pipeline parallelism over a very heterogeneous distributed cloud or set of nodes, compute graph. How about that? In this paper, they're more talking about training. So this paper is not about inference. It's mostly about a training workload, right? And in a training workload, it's different. There's different types of requirements, and it's a training workload on a much more homogeneous compute graph, right? Where you have basically these little islands, and then within each island, it's very, very fast interconnect speeds, and the devices are all basically the same. Okay. So let's learn a little bit more about their system setup. I think we already went through this. No, okay, so DiLoco. So you have a model with some parameters theta, right? So this is each of the 70 billion parameters in a Llama 2. That's what those are there. You have some training data set D with X and Y. X and Y are the input data and target. So this is basically a supervised learning setup, right? Where you have, this is the input to your model, and then the Y is going to be the output of your model. And that target, you're going to say, here's the output of the model, here's the target. I'm going to loss function, and then I'm going to push that gradient and change these thetas. The data set is split across multiple shards. So if you're training on all of ImageNet, you would basically split ImageNet into individual shards and then basically do a type of data parallelism there where train on different subsets of the data set on each of those different islands. We start from an initial model with parameters theta 0, which can be initialized as random if you're training from scratch or using a pre-trained model. You have K workers, each capable of training a model replica and K shards of data, so data parallelism here. There are two optimization processes. You have an outer optimization process, and then you have an inner optimization process. So again, this is a training workload, right? So in this training workload, you're doing feed forward, and then you're doing basically backprop, right? And should I show this? Let's wait a little bit, and then we'll show this. At each outer step T, gradients from each worker are gathered, averaged, and then sent to an outer optimizer to update the shared copy of the parameters. Okay, so every GPU or every TPU in this setup each has a little copy of the model, right? A full copy of the model, right? And then each of those little GPUs is receiving a shard of the data, and it's basically feeding that little mini batch through the model, and then it's getting the output, and then it can say, okay, I'm going to do the backprop, and then I'm going to basically give you the gradient for my specific mini batch on this specific TPU, right? Or this specific node. I'm just going to say node to use the generic term. But all the other nodes, because they're using different shards of data, they're going to get different gradients, right? So they fed a slightly different shard mini batch of data through the same model and got a slightly different gradient, right? They got slightly different little parameter changes, right? So one TPU, which pushed one mini batch from one data shard, says, okay, well, actually this neuron here, you need to actually increase it by this much. And a different TPU, which received a different data mini batch from a different shard, is saying, actually, you need to change this neuron here by this much, right? So what you're going to do is you're going to let all of them compute their mini batch, and then you're going to go and say, okay, well, I'm going to take all the different little deltas that each of them wants, and I'm going to basically combine them. And I'm going to have this outer optimizer that, rather than basically changing the model weights at every single mini batch, I'm going to let all these other ones basically accumulate these gradients, and then I'm going to average all these gradients together, change the actual like kind of shared model, the model that we're all using, and then we're going to send that to all the distributed little nodes. So basically, all the nodes have the same model. They're all computing the gradients with respect to their own slightly different data sets, and then there's a kind of like a master process that is aggregating all the different gradients and then changing the model weights and then sending it all back so that each little individual node now has the new updated model, right? So already you can see the problem with this, right? So the problem with this is that all of them are basically operating in step, right? They basically all need to wait for each other, and they all need to basically wait for the update, right? So all of them are pushing the batch at the same time. All of them are grading the gradients at the same time. They're all sending the gradients to this central outer optimization loop, which is then updating the model parameters and then sending it all the way back to all the different nodes. So if you tried to do this with something like this, it would be absolutely horrendous, right? Because let's say you had one GPU there that was really, really slow. All the other GPUs would be waiting for that one slow GPU to finish in order to all update at the same time, right? But in Google's case, because every single little TPU here in this data center is the exact same fucking TPU, that means that they all take the exact same time to calculate their own little mini batch, and then so it's like everything is, you can put everything in sync because you have this kind of homogeneity at the hardware level, right? So this technique only works if you have like a bajillion TPUs that are all the exact same TPU, and they're all basically taking the same exact amount of time to calculate the gradients from the same size mini batch. Okay. So this outer optimizer updates the shared copy of the parameters, and then this shared copy is then resent to all the little local workers. Okay, within each phase, each worker performs independently and in parallel of its own inner optimization. So each individual little worker, it's almost like doing its own little training, right? It doesn't need to know what the other little TPUs are doing, right? It's doing its own little training loop where it's getting a mini batch of data, pushing it through feed forward, back propagating, getting the gradients, getting another mini batch of data, so on, right? So it has its own little inner loop, and then all of them basically update every H step. So you have this kind of like outer loop, which is running T steps, and then you have this each inner loop, which is running H steps. Each worker samples data from its own shard, right? So that's pulling mini batches from its own shard of the full data set, which you split. You take the full data set and you split it beforehand into these shards, and updates its own local copy of the parameters. Note that the inner optimization consists of H greater than 1 steps, several hundred steps. Therefore, communication across workers is minimal. Right, so each little node here is actually not doing that much communicating to the other ones compared to this, right? In this one, you can't even do one feed forward without communicating because you don't even have the full model, right? So in this situation, this is a model parallelism or kind of a pipeline parallelism where in order to even get the actual final answer, you need to run through a bunch of different GPUs because you don't have the full model. You only have one part of the model, right? Versus in this situation, this is a kind of like a data parallelism. Each individual TPU has the full model. They can basically do the entire training loop themselves. They don't need to communicate anything with the other ones because they don't need the other ones, right? So that's the advantage there. Once all workers have completed their inner optimization step, the cumulative gradients of each worker is averaged, and then the resulting outer gradient is used to update the shared copy of the parameters, which is then used as a starting point for the next round of inner optimizations. This is the only time when communication among workers is required, and it happens once every H inner optimization steps. In total, a worker trains for N equals T times H inner steps. Okay, and this is actually very similar to in reinforcement learning. You also do this kind of thing, right? Where basically you have like a shared model that is basically being distributed out, and then you're pushing gradients into the models and then aggregating those and then sharing it out. So it's like this idea of basically having like the shared model that gets updated with basically the updates from all of the nodes and then gets sent to all of the nodes so that they can then use the slightly more updated model. That pattern is used in RL as well, I guess is what I was trying to say. For the inner optimizer, they use AtomW, and then the outer optimizer, they use Nesterov momentum. And look at this is the Ilya paper. So I have here, I've shown this before, but I really like it. It's visualization of what exactly backpropagation looks like, right? So here on the z-axis, you might have, this is like the actual loss, right? So when you're training, you want the loss to go down, right? And here on the x and y-axis, you might have the values of two neurons, right? So imagine this is just a little neural net that only has 2 neurons, and then the neuron number 1 can have a value of 0.5, and neuron number 2 can have a value of 0.5. So that would mean that you're here, right? And you might have a loss of 2. Whenever you take a gradient step, you're basically changing, you're making a little update to the neurons, right? So you're changing these parameters. Maybe you move a little bit more this way and you move a little bit more this way, which means now you're here, right? So now your neural net is slightly different, and because of that, your loss is slightly different, right? And what these optimization algorithms are doing is they're basically moving in this loss landscape in the direction of the gradient, right? So the gradient is just the slope. They're basically just moving in that direction. And I think this is a little bit better, right? So they're moving from an area of high loss to low loss, right? And in the space that they're moving in is the space of the parameter space. So the problem with this visualization is that it's two-dimensional, right? Or three-dimensional. It's showing you as if this was like a little 2-parameter neural net. But the problem is that we're talking about 7 billion parameters. So this analogy of the ball rolling on the hill, like, it's not actually correct, right? And whenever you're talking about a 7 billion parameter model, like, it's way more complicated than this, but for some reason it still kind of works out, and our intuition from this lower dimensional space kind of still works for 3-dimensional spaces, because what Nesterov and Adam are doing is they're basically adding this momentum term. So what momentum terms are all about is saying that, okay, well, last mini batch I took this step, and then the next mini batch, I take this step. So rather than just kind of individually thinking about each little batch and each gradient update individually, why don't we actually take into account that if the last batch I moved in that direction, I probably should be moving in that direction in general, right? So they have this notion of like momentum, where it's like, if for each batch I keep moving in that direction, there should be this notion of kind of momentum where the next batch, even if it tells me to move backwards, it'll tell me to move backwards less, because there's this kind of accumulated momentum. And you can see how the momentum results in kind of slightly different kind of behavior here. I don't know, I could just watch these all day. Little balls rolling on a hill. Okay. Back to here. When outer opt is SGD, the outer optimizer is equivalent to classical federated averaging. If the total number of outer optimization steps is set to 1, reduces to souping. What a great name. And if H is set to 1, then interop diloco is equivalent to large batch training with data parallelism. Diloco can be interpreted as data parallelism method that requires very little communication, and therefore it can scale to workers that are poorly connected, e.g. workers placed in very distant geographic locations. Workers could, of course, use standard data and model parallelism for their inner optimization. So even within, right, in this case, the nodes that they're talking about are different data centers, but then within these data centers, you could also have different, like, model and data parallelism running in here. So here they make it seem like this is just one TPU and one V100, but here, right, there's 100 TPUs, and each of those TPUs, the way that they might actually be calculating stuff in there might have data parallelism, model parallelism, pipeline parallelism within here. But they're kind of like taking a higher level look at this and saying, okay, well, when we say inner optimizer, outer optimizer here, or workers here, the communication across workers, they're not talking about the communication between the individual TPUs within this data center. They're talking about the communication of this whole kind of like node to this node here, right, where this might be 100 V100s and this might be 1,000 TPU V4s. So the definition of node is a little bit fuzzy there. Okay. Experiments, they largely do this on the C4 dataset. Where we at? We're at 930. Using 8 workers yields lower perplexity. So here they're showing you how this is kind of interesting, because one thing that I've talked about before is that the batch size can sometimes lead to better training, right? So like when you're thinking about this, right, if you were feeding in your data, your training data one at a time, right, the ball on this hill would be kind of bouncing a lot, right? Because each individual data sample is kind of more noisy, right? So like if you feed in your training data one at a time, this ball would kind of be bouncing all over the place, right? If you feed in your data in batches, then the kind of noisiness of each individual data sample gets kind of averaged, right? So the gradient direction of a batch of data is slightly better than the gradient direction of individual pieces of data. And that kind of also has like a similar kind of situation happening here with this diloco, right? Where like when you have this inner loop, outer loop kind of situation, right? The inner loop, they're all on the same data shard. And then the outer loop, it's basically gradients from different data shards. So the outer loop, you don't actually want to be thinking about that the same way as the inner loop, because the outer loop is actually more represented, like the direction of the outer loop is actually going to be better because it's almost like there's more, there's more individual little data points that are contributing to that direction. So you could see how, for example, in the outer loop, you might be more comfortable with the larger learning rate because you're kind of, that direction is the result of lots and lots and lots of little individual points within your training data set. Versus in your inner loop, you're fundamentally coming from less points of your training data set, which means that there's going to be more noise in there, which means that the direction that little marble takes is going to be less certain. It might actually lead you in the wrong direction. So there's kind of an interesting effect there as well, which is, I think, what they were trying to show here, where diloco actually, like, it lowers even faster, right? So you can see here this blue line gets to a lower perplexity, which is kind of like a score, right? So high perplexity is bad, low perplexity is good, and it's showing you that it's not just about being able to train faster because you're doing it in parallel across a lot of devices, but it's like that each individual update to the model parameters is also better because it's actually taking to it's almost like a larger effective batch size, so that it actually ends up being a more consistent and good gradient direction. I don't know if hopefully that kind of made sense for you guys, but I think this is important because it basically means that parallelism is not just about doing things faster because you're splitting it out. It's also like doing things more efficiently because your kind of effective batch size is bigger. Okay. We have searched over the hyperparameters of the outer optimizer. Okay. Is there anything here? We only considered a single task and a single architecture and a transformer. Other data sets and other architectures are known to be more sensitive. This diloco presented here assumes that all workers are homogeneous. However, in practice, workers might operate at wildly different speeds. Waiting for all workers to perform the same number of steps is rather inefficient. So this little sentence here, which is basically a throwaway at the very end of this paper, to me is like the biggest kryptonite, because this waiting for all workers to perform is rather inefficient. That's why this diloco is never going to work for something that's kind of this open source, giant, decentralized mesh of compute, right? This technique is only going to work when you're working inside these data centers where every single thing is the same and all of them can basically take the same amount of time, so you can have a pipeline that has these kind of like all reduces, because they're all reducing at the same time, right? It's not like you're waiting for one machine to finish for the other machine. It's like they're all kind of like operating at the same clock. Damn. Okay. Let's go back here. So should we look at these algorithms, guys? Generating sequence client-side code, replace failed server. So this is input prefix tokens, embeddings, known servers. So here's the list of servers that you have. Streams, chain, find best chain. So here the chain refers to the fact that your servers are being organized in this graph. So each little client, right, is finding the shortest path between the first and last block, as in like this is pipeline parallelism, right? So the entire pipeline is split and it needs to find a actual chain through that graph of possible compute to get to the actual final answer, right? It wants the answer at the very end of the transformer. And it needs to basically find, okay, well, I'm going to use this server to do the first two parts, and then this server to do the next two parts, and then this server to do the next two parts, right? So that's this chain here, is like which chain of servers it's going to call in order to basically get the final answer that it needs. So you can see here how it's like going through all the servers in that chain and then calling, saying, hey, here's the input that you need, little server, to calculate your 3 transformer blocks, and then send me back the answer. And then I'm going to cache that. Right, so you can see here the cache. This is like this notation here is like a map, hash map. So this is like a dictionary in Python, right? So your cache is a dictionary, and then for each server, you're storing the, for example, how long it took to execute that and the network latency that it took to do that as well. Should continue tail servers. While should continue do this. While not empty, do this. Here's where it's maintaining the priority queue. Stream.pop. Replace failed server. Okay, so if you have try catches, so if you have an error, now you're going to have to actually remove that specific server from your little cache here of servers. Okay. This is not a very well written algorithm. There's a lot of crap here that kind of doesn't necessarily need to be here. This one is a little bit cleaner because it's also a little bit simpler. So you have your initial model, you have k workers, you have however many shards for each worker. Each worker is basically one data center. Here's the inner step. So this is what's happening within one data center. Within one data center, you're calculating you're sampling a mini batch of data from the data set, or not from the full data set, from that specific data shard. You're calculating the loss from that, right? So you're doing feed forward and then back prop, and then these are the updated weights. So now you're saying, okay, well, this data center calculated these changes to the weights, and then, okay, now once all my data centers have their little delta, then I'm going to say, okay, for all the workers, aggregate all of that together, update the weights, right? So you get the final delta, average the outer gradients, and then run the outer optimizer, get the final model, and then you're actually, they don't really say it here, but then you're going to use this theta t and then send it to each of these individual workers. So this here, right, this gets updated by the outer loop. The outer loop calculates the new model weights, and then those get sent into the inner loops to then calculate their own little individual mini batches from their individual data shards. Jesus. Let's see. I think these guys had a little bit of parameter efficient fine tuning. So in the Hugging Face paper, they were mostly talking about inference workloads, and in the Google paper, they're talking about training workloads. But here in the inference workloads, right, in the Hugging Face paper, inference workloads and LoRa fine-tuning workloads are actually very similar, right? Because in LoRa fine-tuning, you're basically freezing the pre-trained model so that you're never actually really calculating gradients and doing backpropagation with respect to the actual pre-trained model. You're basically only doing it with respect to the LoRa. So that's a little additional benefit of LoRa fine-tuning. Traditionally, this is done by fine-tuning all models on the downstream task. This is almost never done. I don't know anybody that does this now. Fine-tuning Bloom 176B with Atom requires almost 3 terabytes of GPU memory, which is why nobody does that. Parameter-efficient approaches such as LoRa are often competitive with full model fine-tuning. Not only competitive, they're like better. Another appealing property of these approaches is that they allow rapidly switching a pre-trained LLM between adapters. So this is, we did a stream on SLoRa, which was basically this way of basically maintaining a bunch of different LoRas and then just swapping them in at runtime. So LoRas are good for a lot of reasons. Clients responsible for storing their trainable parameters. So in the server client kind of abstraction that they introduced in this paper, right, the client is going to be the one that stores the LoRas, which is good for also privacy reasons, right? Because then the servers, right, your random decentralized servers, they never really see your full LoRa, right? So you, the client, you have your local fine-tuning data. You're asking the servers to calculate the activations for you so that then you can then backprop through the little LoRas, but the server never, I guess it sees your activation, so it can kind of eventually infer the fine-tuning data set that you have locally, but it's not explicitly storing it, right? So I guess
I guess it doesn't matter because the server is receiving your stuff, so it is going to eventually know what you're training on. But like one of the ideas of federated learning was like kind of privacy reasons where like, right, if all the learning is happening on device and all the device is sending is just like a weight change, like a delta, an update, then maybe the server doesn't know. But the problem with that argument is that you could figure out what that is, right? It's like if I say, okay, I have some secret data, I'm going to make some a gradient update based on that. Here's the gradient update. Well, then the server can just be like, okay, I'm going to take this gradient update and I'm going to run it backwards, and I can just kind of basically infer what your data is. So there's a little bit of like privacy leaking there, but it's better than just having the data explicitly, I guess. They do not update the server parameters, right? Because the server-side parameters are frozen. They're just in a pre-trained frozen state in inference mode. The server treats these values the same as input activations, right? The server doesn't even know that it's a batch of training data. It just thinks it's a batch of data the same as every other data that's coming in, right? Fine-tuning forward and backwards at one go. Do not need to store past implementation details. Okay. So obviously they have Tim Detmers on deck here. So Tim Detmers hooked them up with all the cool quantization stuff. They use quantization, which is basically using lower precision data types to store more total numbers within a GPU, right? Any kind of memory can only store, if you can store one float 32 or two float 16s or three or four float 8s, right? So like the more you quantize each individual number, the more of them you can store. So in this Detmers paper, which I think we read, I'm not exactly sure if we read this one, but there's this kind of like fancy situation where you actually do mixed precision, where you basically he realized that, or they realized, the people who wrote that paper, that if you actually look at all of the model parameters, the model parameters that actually matter the most are these outliers, right? And those outliers, it's worth spending extra bytes to store them at a higher precision, right? So 16-byte or 16-bit for the higher, for the outliers, because they actually end up mattering more, and then lower precision for the normal values because they don't matter as much. We apply dynamic block-wise computation to the hidden states before pipeline parallel communication, which halves the bandwidth requirements with any noticeable effect on generation quality. So this was actually also cool, right? So because in pipeline parallelism, right, you're sending the intermediate values to the next node, right? So here you're calculating the transformer block 1, and then you're sending the output of transformer block 1 as the input to transformer block 2, right? So if you have to send 1,000 numbers that are in float 32, that's just more shit to send than if you have to send 1,000 numbers that are in float 16. So the data type of the actual information, the intermediate activations that you're sending, is actually quite important. And if you use quantization, you can reduce the size of the message that is being passed in this pipeline parallel communication. So it's like a double win, right? So quantization helps you reduce the memory footprint, but it also helps you increase the communication speed because the messages themselves that you're communicating are smaller. Okay. So in this table, they compare their algorithm, right, with caching with restarts, which is kind of just like a baseline. But the important thing to look at here, and this number represents steps per second, which is a way to think about inference, right? And it's actually worse, right? So look at this. So caching with restarts, 17 steps per second. Algorithm 1, 11 steps per second. So you're like, wait a second, it's worse. How their algorithm is worse? What the fuck? This paper's a lie, right? And why is it worse? It's worse because there's all this extra shit that you're doing, right? You're basically calculating, you're maintaining these lists of servers, and you're basically saying, okay, well, this server's fast, this server's slow. Let me ping all the servers and see which one is faster and slower, right? Like all of that costs time. So what are you actually gaining by that? Well, what you're gaining is this, right? So the important thing here is that the failure rate matters, right? So if you have a failure rate of 0, then you don't need any of this like keeping a list of the servers with respect to network speed and blah, 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 because that's just a bunch of overhead, right? And you're going to pay for that. But if your failure rate is high enough, then you need to do that, right? Because if your failure rate is high, then this caching with restarts is absolutely terrible, because as soon as one node fails, then you basically need to restart the entire fucking computation, and that's going to take forever, right? So in this case, if the failure rate is high, then it's fine. You already had you can just go to the next node in your list and you say, okay, well, this server failed. Let me go to the next server that I had that was calculating this specific part of the pipeline, and I'll send it to that, and I'll only need to calculate that. So this entire algorithm is really optimized for higher failure rates, and the higher your failure rate, the more optimal it becomes. But if you have a very low failure rate, such as this situation here with Google, where you have these giant clusters of just the same TPU that basically never fail, then all the overhead that you're doing in this paper is unnecessary. So I don't know, I just thought that this is kind of a great kind of way to visualize how the stuff that they're describing in this paper is actually making your algorithm slower. It's only making it faster when you account for the fact that with a high failure rate, doing all this stuff is worth it. How big is the diff of one of these adapters roughly? Kilobytes, megabytes, or gigabytes? So you can have different LoRa sizes, right? The LoRa adapters or any kind of parameter efficient fine tuning, it depends on what you can choose different parts of a model to change with a LoRa, right? The adapters are specific to the individual parts of the model. So if you have adapters for every single part of a model, then it can be quite big. It can be like gigabytes worth of adapters. But if you only have adapters for some subset of all the model layers and model parameters, then it can be quite small. I would say in practice, Spirabel, it's probably more like megabytes, not gigabytes. But I could see a situation where you have some random bespoke like unit or something like that for a diffusion model, and like the amount of total LoRa, and maybe you have many different LoRas too, so you're adding together a bunch of different LoRas as well. So then in that world, if you have 10 different LoRas for each of the layers, then maybe you can get to like a gigabyte. But I don't know, I think in practice it's more megabyte. And it also depends on the quantization, right? So as they were saying here, if you quantize, what is the precision of your LoRas, right? Like, are you storing your LoRas in full precision, or are you storing it in 4-bit normal float format? Okay. So they did some experiments, and this was kind of a weird experiment that I thought was kind of cool. So they have a computer with a dual Xenon CPU. So these dual CPUs with 4 1080 Ti's, which is like a really old NVIDIA GPU, and then 12 sticks of 64 gigabytes each. Like, what the fuck is this? This is like the weirdest computer I've ever seen. This is a computer with a huge amount of RAM on a very fast, DDR4 is the fastest RAM. There's DDR3 and then so on, right? They're like generations, with very shitty GPUs. So it's like what the fuck is this computer? But okay, so they basically, I think what they were trying to emulate here is a situation where you have a bunch of people all over the internet with weird tiny GPUs, potentially weird setups. So they're trying to make a weird computer here, right? Because they're trying to prove a point that if you have a weird heterogeneous compute mesh where nodes are dropping in and out all the time, and some nodes are very fast, some nodes are very slow, the more weirdness that there is, the better that this paper works. So they're trying to specifically be weird. We use the pipeline parallelism strategy from Megatron DeepSpeed. Megatron is Neuralink's favorite implementation. It's a Frankentrainer. Yeah, exactly. Our algorithm provides reasonable performance in all tested conditions, especially for high failure rates. Okay, blah, blah, blah. Here they have more examples. So here's TPUs. Actually, I don't know if this is a TPU. Maybe. But TPUs with different speeds, different amount of clients, 103090s with a 1 gigabyte bandwidth. So yeah, a bunch of different numbers for all the different possible setups. But again, like I think the TLDR is this. It's basically the more weird your setup, the higher the failure rate, the better this type of this algorithm is going to perform. Algorithm 1, as they call it, because you're doing all this extra overhead in order to account for that. Okay, what else? Number of block replacements per minute, pipeline throughput. What are we talking about here? No load balancing, new servers only. Load balancing algorithms. Time. So you see variable throughput depending on when you're taking stuff online and offline. Basically have these like synthetic workloads. Look at this. They're not even using real. We do not even use real GPUs. We simulate uneven servers throughput programmatically. So it's like fake workloads. And this is kind of a little bit of a tangent here, but like here, right, they're accounting for the speed of each individual server, and then they're also accounting for the network latency of the server. So that's great. I think those are the two most important things, but there's also other variables here, right? Like another important variable is the cost, right? So maybe one server is running in Kazakhstan where they have subsidized energy and it's really cheap, and a different server is running in New York City where the cost of energy is very high, so the overall cost is higher, right? So you could envision a situation where the load balancing algorithm is accounting for the fact that, like, hey, yeah, that server in Kazakhstan takes much longer to send information back and forth, but it's also much cheaper, right? Or, hey, the server in Texas is using natural gas versus the server in, I don't know, like Saudi Arabia is using solar panels, right? So, or even different, right? Hey, this server in China, if we route it through there, there's a 50-50 chance the CCP comes to our house with a bunch of guns and kills us, versus this server over here in Brazil, like they don't have any regulations, they don't give a shit, right? We can send whatever tokens through there. So in this paper, they really, the load balancing algorithms are really only load balancing with respect to basically the latency and then also the actual time that it takes each individual server to do that, and then maybe the memory of each individual server, so like how much it's willing to, how much of the pipeline it can actually use. But I think that it's going to get much more complicated than this, because I think in the future, you're going to have to start considering about the cost. You're going to also have to start thinking about the kind of like geopolitical and like regulatory implications of like using this server versus that server. So there's so many other variables that are going to go into these load balancing algorithms, so that whenever you're running these giant decentralized inference compute meshes, right? Like the actual workloads themselves, right? So like maybe someone who has a bunch of like porn requests, they're not going to get routed through France because France has like anti-porn laws, right? So like there's so many weird little variables like that that these load balancers could take into account that I think that we're not seeing yet. Okay. This is basically just that plot that the higher your failure rate, the better this works. Limitations. Servers hosting the first may use their inputs to recover client data. So this is kind of what I was referring to, is that it's not just the first model block, it's also subsequent model blocks, right? Because if you know the blocks that it went through, you could just basically go backwards and eventually get to the data. So the same way that, right, you can do saliency maps or if you've ever seen like those images where they go backwards through a convnet and they feed in dog, and then you kind of get these weird like AI dogs that are kind of like dream dogs. That's like some of the earliest stuff that people did. But you could basically do the same thing, right? Where you're like, oh, okay, this is the output for this private data. Let me just feed it backwards and I'll see kind of not the exact data that you put in, but like something that's kind of lets me know what that data is. Motivating contributions. Our system may experience an imbalance between supplies, peers who dedicate GPUs to serve model layers, and demand, peers using the service to perform inference. So it's kind of going to be similar to like the early days of pirating, where you basically had torrents, and there was people who seed and then people who leech, right? And like there's going to be this kind of imbalance where there's going to be a lot of people who want to join this decentralized network in order to perform inference or fine-tuning, and there's going to be a lot less people who are like willing to just like, hey, I'm just going to put my GPU out there and I'm going to be paying this energy bill, and I'm just going to basically be serving a bunch of inference for people that I don't know. So unless they figure out some kind of like payment thing that's kind of like built in, right, where like you contribute your GPU to the node and then you get paid somehow per inference, which is actually a startup idea, right? I'm pretty sure there's already startups that do this, but this idea of like you contribute your GPU and then you get paid based on how many inference requests you're serving, and then you as a user have to pay for the inference. So the money still needs to get worked out. And I'm pretty sure there's startups that are basically trying to pitch this idea of like decentralized GPUs where you can get paid for having your GPU used as part of this decentralized compute mesh. Okay. All right, that's basically it. Let me drink some coffee, summarize this. You guys ask any questions, and then we'll go from there. Come train on our 100% organic, thought crime-free GPUs. Yeah, maybe, right? 100% organic GPUs. All right. Was there anything else that I wanted to show here? No. Okay. All right. Here's a summary of the stream. Okay. Today we reviewed, or actually the name of the stream was Distributed Inference and Fine-Tuning. In today's stream, we reviewed two different papers. We reviewed a paper from Hugging Face Yandex, which is basically the Russian Google, called Distributed Inference and Fine-Tuning of Large Language Models Over the Internet from December 13th, 2023. And in this paper, they basically create a system which they call Petals, which is basically a way of performing inference on a very heterogeneous and very faulty compute mesh consisting of a bunch of GPUs that are heterogeneous, right? So different types of GPUs with different amounts of VRAM, different amounts of RAM, different amounts, better CPUs, worse CPUs, better network latency, worse network latency, right? So like a very heterogeneous compute graph that is also constantly changing over time, right? So nodes are dropping out and nodes are dropping in. And the solution that they use is basically a type of pipeline parallelism, which you can basically think of as taking the full pipeline, which consists of basically, for example, a model, right, that has many different transformer blocks, and you're separating this model or this pipeline across a variety of different computers or nodes, right? So maybe this little GPU here is serving only this little chunk of the model, and then you have a different CPU, a different node somewhere else that's serving this little chunk of the model. And the way that they design this system is that there's this idea of like server and clients. So servers are basically nodes that only serve a specific chunk of a model, and they serve it to a bunch of clients who might all be requesting that same type of stuff, right? Versus clients are actual end users that are basically saying, hey, I want to run this particular model, and the clients are basically keeping an internal list of here are all the different servers that are serving all the different parts of the model that I'm interested in, and I'm going to sort them based on basically the speed of each of the servers, and then also the network latency to each of the servers. And then I'm going to be constantly kind of like running this path planning where I'm kind of picking the best chain of servers that serves my particular inference request. And I think this is great because I think this is the beginning of a giant decentralized AI system that is resistant to any kind of fuckery by centralized power and control, right? Because you could have this all over the world. It's going to be very similar to kind of like the Bitcoin miners where there are just too many of them. They're all over the place, so you can't stop them. What else? Okay, the thing I don't like about this is that it's basically very inefficient, right? So the problem with this is that each individual client has to keep track of kind of all these intermediate things. It has to be constantly sending out intermediate activations. It has to be constantly maintaining this kind of list of the servers and which ones are good and which ones are fast. And all that overhead actually results in slower inference. So if you were to just do this all with just one giant machine and you didn't have all this kind of like load balancing and crap going on in the background, you would actually be faster. This only is faster in situations where you have a high failure rate and you have a very heterogeneous compute mesh. But again, I feel like that's actually more often than not going to be the case. The second paper we looked at, and actually in this paper, right, so this is mostly an inference workload, but because parameter efficient fine-tuning with these adapters such as LoRa's is effectively kind of more like inference because you're really only you're treating the pre-trained language model as kind of frozen, so that part of it is really only kind of inference-like, and then you're doing all the fine-tuning and pushing only into your LoRa, which you have locally in your node, your client node. That means that you can basically use this distributed setup for fine-tuning as well, specifically the parameter-efficient LoRa kind of fine-tuning. The second paper we read is a paper out of DeepMind, which came out a week before, called DiLoCo, Distributed Low Communication Training of Large Language Models. This is basically the type of training that they used for Gemini, because in Gemini they mentioned that they basically train over a variety of different data centers. And in this paper, this is not about inference. This paper is more about a training workload, and specifically, they leverage the fact that their compute mesh or compute graph is much more homogeneous, right? So like within each of the different workers here, this worker here, this little American flag, might correspond to an American data center, which has basically whatever 2,000 of these TPU v4s, and they're all the exact same TPU v4, right? So because they're in a much more homogeneous setting, they can basically have these more synchronized kind of workloads where what they do is they shard a data set, they split a data set into little sub data sets, and then each of these individual worker nodes receives a different piece, a different shard of that data, and then each of those little worker nodes basically trains on that little individual shard of data and then sends every X amount of time an update. So every X amount of time, I think they use the T time steps for the outer loop and then H time steps for the inner loop. So every H inner steps, the individual worker node is going to say, okay, I did a bunch of training with my little data shard or data set shard, and I got to these model parameters. I'm going to send those model parameters, those updated, right, the little gradients, I'm going to send them back up to the outer loop, and then the outer loop, which is happening here, this outer optimization, is going to sit there and it's going to basically receive gradient updates from these different workers. And then it's going to say, okay, here's what each of these little workers got to in their little gradient updates, right? So each of the little workers has a slightly different little path, slightly different path that it took through this loss landscape. And then it's going to basically average them all together and then say, okay, I averaged all the little updates that each of my little workers did. I'm going to average them together into one final update, and then I'm going to send I'm going to apply that final update. I'm going to update the parameters of my model, and then I'm going to send the new model to all my little workers. So basically, this is more of a kind of a data parallelism that is leveraging the fact that it's a very homogeneous compute mesh so that it can have a very synchronized kind of workload that really requires all of them to kind of work at the same time, because if you have any of them that are significantly faster than the other ones, then you're going to have to sit there and wait to receive this outer loop, right? The outer loop has to wait for all the inner loops to finish, right? So this is really the problem here, right? Is that you have a for loop inside a for loop, where basically this for loop here, you need to do all of these workers before you can do the outer loop. So if any of these workers is really slow, you're fucked, because then all the fast workers are going to have to wait for the slow worker. So as long as all these workers are relatively fast and all the same speed, then you're fine, right? Because none of them are going to have to be working for the other ones. So that's basically this. It works great if you have a huge homogeneous compute cloud, and it's a great way to do training if you're doing it in that way. And also they have some interesting plots to show that it's not just, you don't just get a benefit from speed, you also get kind of a benefit from the fact that this is almost like effectively having a larger batch size. So it's like the gradient steps you're taking here are not just like more distributed, they're actually just kind of like even better gradient steps. You kind of get to the final answer a little bit quicker anyways, because it's kind of hard to like visualize, but think about like averaging together like a bunch of different steps from a bunch of different workers. You end up at the final solution a little bit faster than if you would have just like kind of taken a bunch of those steps sequentially. But the negative of this, right, is that waiting for all workers to perform the same number of steps is rather inefficient, and that's why this type of technique is really only going to work if you have a bunch of similar machines that are all relatively fast. But that's the case of your DeepMind, right? If you're DeepMind, you're training on your own TPUs in your own data centers, and you know exactly what's going on. So very different kind of setup than you have here. But that's basically it, guys. We have 2 papers, which I think are pretty good papers, pretty representative of kind of what training and inference looks like in a specifically distributed over these very complicated compute meshes, and how the different types of compute graphs or compute meshes, however you want to call them, the different types and the intricacies and details of those lead to different types of strategies in terms of like what the most efficient way to perform computation is on them. And as they mentioned in this paper here, right, it's like we're living in a world where performance is scaling with model size and data set size and the training time. So it's only going to people are only going to want to train on more and more computers and bigger models. And that's why we're going to have even more model parallelism. We're going to have even more data parallelism and all the types of parallelism, because the GPUs aren't going to get bigger faster than our desire to train bigger things is going to get bigger. But that's it, guys. We're a little bit over. I lost track of the time. Thanks, XR7. Thanks, SHZ, Ed, Minotaur, Ed, Josh, Spyro. Thanks, everybody, for listening. Tomorrow we have a stream on depth models. So if you're interested kind of more in computer vision stuff, that's where we're going to be going over some depth models, which are pretty, but very different from this type of stuff. So hopefully you find that interesting. If not, have a great day, have a great weekend, and see you guys later.